So I'm David. I'm collaborated with Los Alamos National Lab under Pat McCormick. That's how I'm affiliated at Northwestern. So my niche is I like unique heterogeneous architectures and actually how to like program them. So don't think your GPU, but like this talks about processing in memory, but like CG arrays and other architectures is some of my research that I've explored. But this talk is really focused on like we don't like the data movement bottleneck. It kind of sucks. So you have your typical compute-centric architecture, and what processing and memory and what this talk is talking about will disrupt that and do some compute within the memory sector. So what exactly is processing and memory? So it's either near or in memory, and it's all about reducing critical path length by adding more simple cores, right? These smaller cores, and they have their own local memories, and you have a lot of them on your single node cluster. So you have a high degree of parallelism, but you get this reduced critical path length to increase efficiency. So you get better energy reductions, and your total cost of running your server will decrease because you're spending less on energy. Some of the workloads that have been explored is like genomics and AI. So it's like, how do you fit this to HPC? That's kind of the question. There's a few different solutions that exist. This talk is focused on a DRAM solution. So it's like an in-place drop-in replacement. Instead of your typical DDR4, you have your drop-in replacement of the DRAM. There's other solutions like high bandwidth memory that you could drop in and replace that. Samsung has worked on that where it will speed up your GPU kernel computation. So there's just a picture of like some of theirs. They're taking a very heterogeneous approach to PIM. So just speeding up all these different things. But yeah, PIM-enabled memory. So the specific hardware solution that we've used is UpMem. UpMem is comprised, it's a drop-in DIMM replacement with 128 processors on a single DIMM. Each of these GPUs have 24 hardware threads, and they're a 32-bit RISC style instruction set architecture, right? They're not RISC-V or anything like that, but RISC style with 64-bit capabilities through emulation. So if you have a single socket server, you could have 40 ranks per, let's imagine you have 40 ranks on that single socket server, and it supports 64 GPUs per rank. So you multiply that out, you get 2560 GPUs per single socket server. And that's really the hardware configuration that we're testing with. So what is this architecture? It's really, there are limitations, of course. It is more of a research product than anything else. So one of the limitations I'll address here is you still need a notion of host memory that's separate from the device memory. So that comes into like the accelerator model. Within each of these PIM chips that we see, like I mentioned, you have that 24 different threads. And all of these threads share a main RAM that you could see that on the right-hand side, that green. So that's MRAM. It's to keep in mind the size of these things, 64 megabytes shared amongst 24 threads. And then it has a 64 kilobyte cache. So you load and store things from the main RAM into the WRAM. And then there's a 13-stage pipeline. And you could saturate that with about 11 of those threads. So let's talk about some more limitations of this researchy software or architecture. So another big limitation, as you can see here, no floating point, and also lack of a communication network across these different processors. So these are very small processors, and they can't directly communicate to each other because they're using your standard DDR4 communication network. So in order for one processor to communicate to another one, you have to go through the host. That's a big, you don't want to do that, but you have to with this. So how do you program? Like I mentioned, it's similar to an accelerator model, but it's a little different. But in this diagram, I'm basically showing the accelerator model. The host code will do memory transfers, kernel invocations, and synchronization primitives. That's all through their API. And then there's a hardware backend. If you don't have their hardware, they also provide a functional simulator. And then you have the notion of your GPU code. They have their own compiler. That's just an LLVM fork with a GPU target. And then there's an entire runtime. Like I mentioned earlier, there's no floating point. So how do you actually do that? They have floating point emulation, but there's also other related works in order to speed that up because integer floating point emulation is not fast. And people have like looked at interpolation techniques, lookup tables, and that kind of stuff in order to speed up floating point computation because integer emulation is not fast. It's not fast. So putting that all together, you have the API that will execute on or invoke the DPU code, and then it will run on the various backends. So looking back at the overall question, how well does the Legion task model map onto processing memory architectures? This is taken directly from the Legion website front page. It's a good quote, right? Like if you want high performance and power efficiency, you need a good programming system that cares about the placement and movement of data, right? That's really what inspired me to map this architecture utilizing Legion because it there's that huge limitation of that communication network. So if we could overlap computation communication, we could get potential speedups compared to the other related works that program this architecture. So like I mentioned, Legion utilizes large task graphs to minimize kernel invocation and communication latencies. So how do we support this in the Realm backend? We created a processor, a DPU proc, that's what we called it. Basically, there's one of these processors per DPU. So these processors are very fine granularity. So this is something that needs to be evaluated in our future work because very fine granularity, there's a lot of overheads that are potential there that I haven't looked into as much yet. There is also the notion of the MRAM memory. So that has affinity to the host and it'll do the necessary data transfers to put the data in place where it needs to go. And UpMem's API has synchronization primitives that we've implemented with their callbacks. There's function callbacks to figure out when events are basically done. And then that's how we could handle forward progress within our application. And then, yeah, we've added to the default mapper to allow for your typical equi-partitioning of index-based task launches. Like I mentioned, this is a work in progress. Some of the good, the UpMem DPUs are controlled by Legion and Realm host code. There's that forward progress that I mentioned. We could launch kernels, transfer data, and we can also read and write data from the device side of things. So we haven't changed the Legion programming model. You could use Legion iterators on your device code, and that's really good. However, we're not able to scale just yet past 64 of these DPUs, and that's just, I've spoke to Elliot about this, but it's due to a mapping address bug. So these are physically addressed devices, starting from 0 going to 64 megabytes, and then there's multiple of them, hundreds of them. So there's something wrong there. And I haven't really tested any complex collective communication patterns. And also I needed to test some larger applications. But yeah, so some of the related work that's the state of the art that we're comparing against is basically this work called Simple PIM from ETH Zurich. They have an entire model abstraction of data types that are arbitrary size dimensions and any size, any dimension. They provide abstraction for writing host code and the device code. So you just work on these arbitrary sized arrays. It does the collective communication for you, that kind of thing. And it does some sort of optimizations to device code as well. So the best state of the art, these are very small micro benchmark. This is a micro benchmark, so take it with a grain of salt, but we're going to compare against that because that's what I have running at the moment as this is a work in progress. But so simple PIM, you can see as they scale, I would look at the wall clock time in seconds and versus Legion, it's a very similar which is surprising for being a micro benchmark. It's not a huge degree of overhead as I was expecting because Pat was telling me a bunch of times is there would be a high degree of overhead, but it's not as bad. And what our goal is to scale to thousands of processors, and hopefully we get some better speed up than the prior state of the art work. So some of my experience here, it was a lot more engineering effort than I anticipated, unfortunately. So how Realm handles like stuff, NVCC is so nice. I don't have that. So I can't like static link host code and stuff like that and that kind of thing. So I don't have the ability to get C++ because I don't even have all the C headers. So I can't even compile C++. That's great. Um, so like I mentioned before, the runtime overhead due to the granularity of the processor, that's also an issue that needs to be evaluated. Um, and then, as I mentioned, the physical addressing. So some of the future work is really scaling across on a single node. So single node, the 2560 GPUs, and then porting more complex benchmarks. And then we want to do multi-node test. However, there is no multi-node upmem cluster. So my thing is they provide a functional simulator, of course, and we could estimate what performance is like on a single node, like how long it takes for a kernel to run on a single node. So we could kind of create some sort of regression model that varies selectivity parameters to estimate what it's like to run on a multi-node cluster. Because like the communication is real, but just the execution of the kernels isn't. Um, but yeah, lightning talk. Does anybody have any questions?